Right, let's have a look at some examples. Now it says here, let x denote the height or the heights in meters of pupils at a certain school. Okay, so x is a random variable. It denotes the population because we're talking of the heights of the pupils at a certain school. So clearly it's all the pupils in the school. Okay, so that will be my population. If x is normally distributed with a mean of 1.4 meters and a standard deviation of 0.15 meters, what proportion of students are between 1.1 and 1.7 meters tall? The starting point for this will be to look at the distribution. It says that x is normally distributed. So graphically this is what we have, and always the mean will be in the middle. Okay, so this is really the first step of all of these types of calculations. You should draw the curve first and indicate everything, all the information on the curve before you actually go ahead and do any calculations. This will help with your understanding of the problem. Right, so x is normally distributed. It has a mean of 1.4. So that's the next step. Mean of 1.4, standard deviation of 0.15. So if we indicate this, then the middle point, which is the mean, will be 1.4. And I'm going to just write here that x is normally distributed with a mean of 1.4 and a standard deviation of 0.15. Of course, this is the variance because it's 0.15 squared. Then, what proportion of students are between 1.1 and 1.7 meters tall? Well, 1.1 will be below 1.4. So here's the cutoff point, and 1.7 will be above. So we're interested in the number, or rather the proportion of students that lie between these 2 points. So we're interested in that area over there. So in the terms of our notation, we will write it as P in brackets 1.1 less than x less than 1.7. Okay, the probability of x being between 1.1 and 1.7. Now I'm going to solve this using a CDF because I don't want to integrate. Remember, the normal distribution doesn't have a very nice looking PDF, and if I have to integrate from 1.1 to 1.7, it's going to be quite a task. But I want to use my CDF. So in this case, I'll take everything up to 1.7 and I'll subtract everything up to 1.1. Okay, so that means the entire blue area is what I'll calculate first, and then I'll calculate the size of the black area there, and then I'll subtract the one from the other. So if we look at the blue area, and the first step will be to calculate my z-score. Remember, everything works in terms of distance. This point is 1.7 meters and the midpoint is 1.4 meters. So I want to see how many standard deviations am I away from the mean. So I'll take 1.7 minus 1.4 divided by 0.15, and that means I am 2 standard deviations above the mean, because this is plus 2 or positive 2. And my z-score, well, that just denotes the number of standard deviations. So what I'll do is I'll say the probability of being less than so many standard deviations, which is the blue area. That means z will be less than 2 standard deviations, okay, because if this is 2 standard deviations, I'm looking at everything less than 2 standard deviations. And using my empirical rule, 2 standard deviations will give me a probability of 0.975. Okay, 1 standard deviation, 2 standard deviations, and we know that 2 standard deviations contains 95%. Okay, 95% in the middle. So by symmetry, that means 2.5%, 2.5%. So 95% plus 2.5%, that will give me 97.5%. Right, next will be the black area. So the total area I'll calculate by first looking at how many standard deviations am I away from the mean. So it's 1.1 minus 1.4 over 0.15. So that gives me negative 2. Okay, negative 2 because I'm 2 standard deviations below the mean. The signs are really important here. So I'm 2 standard deviations below the mean. So that means negative 2. And I'm interested in the probability of being less than 2 standard deviations below the mean. So again, by symmetry, I know using the empirical rule that this is probability 0.025 or 2.5%. Subtracting the black one from the blue one, I get 0.95, which is the area that I wanted. Let x denote the heights in meters of pupils at a certain school. X is still normally distributed with a mean of 1.4 meters and a standard deviation of 0.15. What is the probability that a randomly selected person is shorter than 1.65 meters? So again, normally distributed, we'll draw the curve, standard deviation and the mean, So we'll indicate that mean is in the middle, 1.4, and I'll just write here my distribution where I have my standard deviation. Remember, I'm squaring it, so that means that I'm actually calculating the variance here, but 0.15 is my standard deviation. I'm interested in shorter than 1.65. So if this is 1.65, I'm looking at being below it. So I want the size of this area over here, which will be the probability. So first step will be, how many standard deviations am I away from the mean? Okay, so how many standard deviations is this 1.65 away from the mean? So that means I need to calculate my z-score. And my z-score is nothing but 1.65 minus 1.4 divided by 0.15, which is equal to 1.67. Now this is actually 1.6 recurring, but I rounded it to 2 decimal places. Okay, so just showing the calculation over here where I'm actually needing it. I have a z-score of 1.67 rounded to 2 decimals. Now I'm interested in the probability of being less than 1.65. Okay, so for x to be less than 1.65, it means that my z-score must be less than 1.67. Okay, so I must be below 1.67 standard deviations from the mean. Okay, this is 1.67 standard deviations. I must be below it. Now, the empirical rule doesn't help us here because this is 1.67, and the empirical rule only gives us information for 1, 2, and 3 standard deviations. Nothing about decimal standard deviations, okay, or parts of a standard deviation, because this is saying 1 and 0.67 parts of a standard deviation. So what we'll do is we'll have to use our z-score tables. Now the z-score tables are really easy to use. In this case, we're interested in finding a z-score of 1.67 because we want to know what is the cumulative probability associated with it. Okay, this table, our z-score table, or our standard normal table, or our z-table, or our cumulative normal table, whatever you want to call it, it contains cumulative probabilities. So you can see if we start here, z being 0, okay, now where will z be 0? Well, if this is my normal distribution, then z is in the middle, then mu, is in the middle. So if I have an x value that is equal to mu, how many standard deviations is x away from mu? Well, if x is equal to mu, then x minus mu over sigma is equal to 0. Okay, so that means 0 standard deviations away will give me a probability of 50%, which simply means that if I'm sitting at the mean, then I have 50% of the data to the left of the mean. And as I move further above the mean, I'm accumulating more and more probability. So you can see as I move from this value over here, okay, where z is 0, 0, and the z becomes bigger and bigger. Here it's already 2. Here the probability increases to 0.9811. Now the z-score is split into 2 parts on the table. The first column contains the integer part and the first decimal, and the first row contains the second and third decimals, or in some cases just the second decimal. So 1.67 is split up into 1.6 over here. So there I have 1.6. Okay, there's my 1.6. And then the 7 is actually 0.07, and I'll look for it here in the first row. So there it is, 0.07. Okay, so I've identified those two, and just like before, I'll look at where these two intersect. I'll come down, so it's going to be that value over there, which is 0.9525. So the probability of being less than 1.65 meters is the same as the probability of being less than 1.67 standard deviations above the mean, and that's approximately 0.9525 or 95.25%. So if I randomly select a person from the school, the probability or the chances that they're shorter than 1.65 meters is 95.25%. I'm saying approximately because remember this z-score was rounded to 2 decimal places. Okay, so because I've rounded here, the result that I have is an approximation. Right, so going back to my actual image, that means that this shaded area is 95.25%. Let x denote the heights of pupils. It's still normally distributed with a mean of 1.4 and a standard deviation of 0.15. What's the probability that a randomly selected person is taller than 1.35 meters? So graphically, that's what we have. Still the normal curve with the same information as before. But now we're interested in the area to the right. So 1.35 is this cutoff point over here, and we're interested in what proportion or what percentage of people is sitting above that. Okay, so what percentage of people is sitting over here? These are the number of people, okay, and their heights, and here we'll have the percentage of that people. Right, so the first thing is, how many standard deviations is 1.35 from the mean? So if we calculate the number of standard deviations with the z-score, 1.35 minus 1.4 divided by 0.15, you should be used to this by now, that gives us negative 0.33. So determining the probability of a measurement being greater than 1.35 meters is the same as saying I need to be above negative 0.33 standard deviations. Okay, so this over here, we can see it as either being 1.35 meters, or we can see it as being 0.33 standard deviations below the mean. Now again, the empirical rule doesn't help us here, because the empirical rule is just for 1, 2, and 3 standard deviations, and this is a fraction. So we need to use our z-tables. However, because the z-tables are cumulative, I'm not going to find greater than on the table. I need to take the complement of this. So it's 1 minus z less than negative 0.33. So I'm going to find this purple area on the table, and then I'm going to subtract it from 1, and then I'm going to get the blue area as my result. So if we do that, then we'll go to our z-table. We'll look for negative 0.33. Now here we have negative 0.3. Remember, the very first column contains the whole number part of the z-score and the first decimal, and then the first row contains the second and third decimal. So here we have negative 0.3, here we have 0.03, and if we look at where it intersects, then we have 0.3707. So that means 1 minus 0.3707 will give us 0.6293 or 62.93%. Now I'm saying here again approximately because this negative 0.33 is rounded to 2 decimal places. Right, so graphically we calculated the purple part, subtracting it we get the blue part, which is the probability of being greater than 1.35. Okay, and that was 62.93%. Right, now the next example looks at how to find a percentile. So again, we're still with the heights in meters of the pupils at a certain school. It's still normally distributed, it still has a mean of 1.4 meters, and it still has a standard deviation of 0.15 meters. In this case, we're looking at what is the 75th percentile. Now if we take the information that's available, normally distributed, the mean, the standard deviation, and we plot it, we see that it still is the same normal curve that we're working with. Now in this case, we want to find the 75th percentile. Now I said earlier that we'll find percentiles by using the CDF. Now in this case we don't have the CDF, we have the PDF, but let's see what it means. The 75th percentile is simply the value, which we'll call P subscript 75, that separates the lowest 75% from the top 25%. So this shaded area here is 0.75 probability, or 75%. And we want to find this P75 value. So the first thing is, again with the standard deviations, Z subscript 0.75. This is the notation that we will use if we want to find the z-score for a certain percentage of values. Now we don't know what the z-score is in this case, but we know that it must separate the lowest 75% from the top 25%. Okay, so I want the z-score, and I want the number of standard deviations with the subscript 0.75. Now I'm not going to use the notation P subscript 75, I want to use the notation X subscript 0.75. Okay, because this means that I'm calculating the X value for 75%, and the X value will be the one that is measured in meters. Okay, remember Z just tells us how many standard deviations, but X is actually the measurement in meters. Right, so the calculation that we usually use to calculate the z-score is by taking x, subtracting mu, dividing by sigma. Okay, so we're taking how far this point is from the mean, and then we're dividing it by sigma, which will give us a number of standard deviations. In other words, our z-score. So we're interested in the probability of z being less than or equal to this value over here. But we don't know what that value is, we just know that it separates 75% of the data. This smaller 75%. So this is very useful because now I know that this z-score has 0.75 area to its left. So that means if I go to my normal table, then I can just look for 0.75 on the table. Okay, just 0.7505 is the closest I can get to 75%. Okay, so this is an approximation. Unfortunately, the table doesn't contain 0.75. So I'll take 0.705, which is the cumulative probability, in other words, the cumulative area on the left, and I'll just look for the corresponding z-scores. So what I'm effectively doing here is I'm working backwards from what I did previously. Previously I had the z-score, and then I looked for the parts of the z-score on the first column and the first row, and I look at where the column and the row intersects. And now I'm working backwards because I'm finding the probability, or the cumulative probability, and I'm looking at what row and what column the z-score appears, and I see that it is 0.676. And again, I'm saying approximately because this is not exactly 75%. So now that we have the z-score, we can work backwards to calculate the x value, which will be the cutoff point, in meters, which is the units that we require in our problem. So substituting all the values that we have, we can see in our z-score calculation, we need z, x, mu, and sigma, but x is the one that we want to calculate, so we'll substitute mu, which is 1.4, sigma, which is 0.15, and we'll equate that to our z-score, which is 0.676, and solving that we get 1.5014. So that means that the x value over here, which is equivalent to the z-score of 0.676 standard deviations, our x value is 1.5014 meters. Okay, remember the x1 is in meters. Now we know that our calculation is correct because 1.5 meters is greater than 1.4 meters, and the value that we need is in fact on the right hand side, in other words greater than 1.4. It says here, your company packages sugar in 1 kilogram packets. Let x be the weights of the packets, and assume that x is normally distributed with a mean of 1.01 kilograms and a standard deviation of 0.02 kilograms. In other words, x is normal with parameters 1.01 and 0.02 squared. Okay, this is the standard deviation, so squaring it gives us the variance. The question is, what is P20? In other words, what is the 20th percentile? So graphically, if we draw the information, then we have our bell-shaped curve. We have the middle point being 1.01, and of course that will be in kilograms, and I just wrote the other information here at the top. Right, now we're interested in the 20th percentile, so P20, so that means what value has 20% of the observations less than or equal to it. So what we'll do is we will look again at the number of standard deviations. So we want our z-score for 20%. So that means we want the probability of being less than z to be 0.02, or rather, sorry, 0.2. So going to our normal table, again working backwards, we look for 0.2 on the table, in other words 20% on the table. The closest I can get is 0.2005. Okay, it doesn't have exactly 20% on the table. So working back, we see that the z-score will be negative 0.8 and 0.040. So combining the two parts of the z-score gives us negative 0.84. And this negative 0.84 is the z-score that separates 20% of the data, rather the lowest 20% of the data, from the rest. So graphically, this negative 0.84 is the z-score at this point over here. Okay, so that means I need a value that is 0.84 standard deviations below the mean, and that value will separate the lowest 20% of the data from the rest. So if I look at my z-score calculation, then it's just a matter of plugging in the relevant values. I have negative 0.84, which is my actual z-score. I have the mean, which I subtract from my unknown value. I have the standard deviation, which I divide by. And now, seeing as I have the z-score and these two, I can calculate the unknown value, which will be my 20th percentile. And I see that it is 0.9932 kilograms. So this is my x value. And I see that I'm on the right track because 0.9932 kilograms is below 1.01 kilograms, which makes sense because 1.01 kilograms separates 50% at the bottom from 50% at the top. But I'm only interested in 20% at the bottom, so that means my cutoff point will be less than 1.01 kilograms, and in fact it is 0.9932.